Hey guys, in this video we're going to talk about buffers. So we're going to first explain what a buffer is, how it works, and then how to take the pH of that. Later on in class we're going to talk about some other things as well, but I'm going to save that for class. So I just want to give you like a good introduction of buffers now. So first of all, if you remember from your titration curves, in the titration curve video, we talked about there's a section in the curve that is called the buffer region. So this, where your pH is kind of resisting that change, or your pH is resisting a change, that is known as a buffer region. We also have a buffer region when we mix a weak base and a strong acid. If you notice here, this curve represents a weak acid as my analyte and a strong base as my titrant. So my buffer region appears right here. For this titration curve, we have a weak base as my analyte and a strong acid as my titrant. So our buffer region is going to be right there. It's always right at the beginning before you reach your equivalence point. That is where your buffer region lies. So we've kind of labeled that and talked about that is the buffer region, but now let's get deeper into what a buffer is and how we can figure out the pH there and whatnot. So first of all, the question is, what is a buffer? Well, a buffer is a combination of a weak either acid or base and its conjugate. So it can be a combination of a weak acid with its conjugate base. Both have to be present there in order to have a buffer. An example of a weak acid with its conjugate base is acetic acid, which is HC2H3O2. That would be your weak acid component, and C2H3O2 minus. C2H3O2 minus is a conjugate base because it's what is left over after an H plus has been given off. So if I have both of these components floating around in a solution, then I have a buffer. Another type of buffer we have is a weak base with its conjugate acid. So weak base, an example of that is ammonia, and the conjugate acid of ammonia is NH4 plus. Remember, a conjugate acid has added on an H plus to the base. So this is the conjugate acid component. If I have a combination of both of these present in one solution, then I have a buffer there. Notice how I didn't say anything about the strong acids, right? A buffer has to be weak with its conjugate. It cannot have any strong acids or bases in there. So it has to be a weak acid with its conjugate base or a weak base with its conjugate acid. Another thing that you can look out for if you see like a salt, because if you remember from our previous lecture about salts, a conjugate base or a conjugate acid is a salt. A salt conjugate base here would be sodium acetate rather than just the acetate ion. A conjugate acid salt here would be ammonium chloride rather than just the ammonium. So when you see salts, those are your conjugate bases and conjugate acids. And when they're paired with a weak acid or weak base in the same solution, then you have a buffer. So now that we know kind of what makes a buffer, let's talk about what is the purpose of a buffer. Well, the purpose of a buffer is to resist a change in pH. If you look here at this titration curve, and if you did the lab, especially double period did the lab where they actually put a pH probe in there, you notice that the pH took a long time before it started to change, right? Well, that is because when I'm adding a strong acid or a strong base into a buffer, it does not change its pH. You have to completely deplete the buffer, get rid of the buffer, before that pH can start to spike. So that's why we no longer have a buffer region where we see the pH spike. Basically, we've gotten rid of all the buffer that we had present there. So it resists a change in pH. Now, how does it do this? Why is this happening? I'm going to get to a really detailed portion of how a buffer works, but right now, it's just A buffer has both an acid and a base present there, right? You have a weak acid with a conjugate base, or you have a weak base with a conjugate acid. Well, because you have both an acid and a base present, the acid portion can neutralize any base that comes into the buffer. The base can neutralize any acid invader that comes in, any acid that you add to that. So you basically have like neutralization reactions that can happen on both ends. Like you have acid there, so if the base comes in, the acid can neutralize it. But then you also have a base component in your buffer. So if you have an acid coming into your buffer, then you have the base to neutralize it as well. I like to think of it as like an army, right? Like, so I have acid people that can fight off my bases, and I have base things that can fight off my acids. So very important to kind of see if some sort of analogy so you can understand what it means. So let me give you an example of a buffer. There are several different systems in our body that contain buffers. Blood is one of those systems. So our blood has to maintain a pH of 7.4. And because it has to maintain a pH of 7.4, we naturally have a buffer in our bloodstream. And the buffer contains carbonic acid, which is H2CO3, and hydrogen carbonate, HCO3 minus. If we didn't have a buffer in our bloodstream, then anytime anything that is acidic or basic even comes in contact with our bloodstream, then we could get something called acidosis, which means the pH in our blood is way too acidic, or alkalosis, which means the pH in our blood is way too basic. And that can actually make us sick, and it could even result in death. So it's very important that we maintain that buffer in our blood system. You also have buffers in your digestive system. Those buffers are mainly more acidic, like stomach acid and stuff like that. So we have to maintain a very low pH in our stomach so we can digest things properly. So we have lots of different buffer systems in our body. We also use a lot of buffer things for when we're extracting DNA in like biology and biomed. Probably some of the labs that you've done in biomed have used a buffer solution there as well. So I'm going to pause for a minute, and I'm going to get you guys a good little diagram here so we can figure out exactly how a buffer works. All right, so what I have here is we're under the section how a buffer works. So I'm drawing some beautiful diagrams here. It is so hard to write with this pen. So we have the first container is I have a buffer present here. Now, first of all, how do I know that I have a buffer present? Well, I have HC2H3O2. So all of this section here is the weak acid. And on the other side, I have C2H3O2 minus. That's the conjugate base. So because I have a weak acid and a conjugate base present, then that means that I have a buffer here. So a buffer's job is to resist the change in pH. So let's figure out how it does that. If I add strong acid, so in this container, I'm adding a strong acid. That strong acid is in the form of HCl. It is going to have one of these components neutralize that. And so what I mean by that is that basically I'm going to have a reaction between this strong acid and one of these things, either the conjugate base portion or the weak acid portion. So HCl, if I put it in water, because it's a strong acid, it's going to dissociate, right? It's going to be H plus and it's going to be Cl minus that it's going to dissociate into. When it comes in contact with the water, which one do you think that is going to react with the acid? Do you think another acid is going to react with this acid, or do you think the base is going to react with the acid? Well, hopefully you set the base, because bases and acids, they react together. They neutralize to form water, right? So what I'm actually going to see here is that this acid is going to react with the base component of the buffer. And when it does so, let's figure out what it's going to make. So the H plus and the C2H3O2 minus is going to come together. So we'll have H, C2H3O2 that's produced. The Cl minus here is just a spectator ion. So it's going to be floating around in the water, but just not behaving. It's just kind of chilling in the solution there. Okay, so I have a mistake. My bad. Let me catch it first. Let me fix this. It's not going to be minus. It's just going to be HC2H3O2. The reason for that, there's the negative ion, positive ion. They're going to crisscross and cancel out. Okay, sorry for that. I was getting too caught up in Cl minus. So we have Cl minus is a spectator. It's not really participating in the reaction, but we have H plus C2H3O2 minus is going to form HC2H3O2. Now let's think back to what pH is. pH changes when you have H plus concentrations, right? Well, if I didn't have a buffer here, I would have some H pluses floating around. But because this base component is reacting with the H plus to form a weak acid, then that is why my pH is not changing drastically. Will it change a little bit? Yes. What will it do? Will it get more acidic or will it get more basic? Well, look here now. I have 1, 2, 3, 4, 5 weak acid parts. And I only have now, you see how this has been neutralized, right? This had reacted to this. So now I only have 3 of my conjugate bases. So if I have 5 of the weak acid parts and only 3 of the conjugate base parts, then what's going to happen is my pH is going to drop down just a smidge. Okay, it's not going to be a drastic jump. It's just going to barely go down. All right, so that is what's happening when we add a strong acid to a buffer. If we add a strong base to our buffer, which is what you see on the right-hand side, this is what's happening. NaOH is a strong base, right? So it'll be Na plus and OH minus that you have floating around in here. Now the sodium, just like the chlorine here, is a spectator, so we're not really worried about that. What we're worried about is the OH. One of these components, this is a buffer because it's a weak acid, we have a conjugate base here. One of these components is going to react with the OH once it enters the solution. So which one do you think it will be? Since the OH is a base, then that means the acid component is going to react with this. So we're going to have a neutralization reaction here. You're neutralizing this OH that you have coming in there. When that is the case, what it is going to form is the OH and the H here. This is my acid. It's giving a proton, right? Is going to come together to form water. And what I have in addition to water is C2H3O2 minus. Just like before, remember how we said that these have reacted, so they're like not in the solution anymore. I've produced this. Same thing here. This is no longer in the solution. What I've replaced with that, what I've produced instead, is water and C2H3O2 minus. So now I have neutralized my base, my invader that's coming in, and I've done that using my weak acid to react. What will happen to the pH? Well, because now I have 1, 2, 3, 4, 5 conjugate bases for every 1, 2, 3 weak acids, my pH is going to move up just a smidge. Is it going to be a drastic change? No, because that's what a purpose of a buffer does. It resists the change in pH. It's not allowing this OH to be floating around in solution and therefore increase my pH drastically. It's only going to be a small increase because I have more conjugate base than weak acid present here now. Here, my pH went down a smidge because I have more weak acid than my conjugate base present. So this is how a buffer works. Please tell me if you do not understand this concept. I have little cutouts that we can work with in class if you need further help with this. It's very important to understand how these buffers work conceptually. So the next part we're going to go into is how to prepare a buffer and buffer capacity, and then we're going to talk about pH of buffers. So let me get my sheet set up for that. All right, so now let's talk about how to prepare a buffer. You guys are going to be doing a lab where you're making your own buffer and then testing it and doing some calculations. So very important to pay close attention to this. They also like to ask this in free response type questions. So how you prepare a buffer is depending upon what you are given. Okay, so if in a free response question, they tell you that you have both the weak acid and the conjugate base, so you basically have the weak component and the conjugate component. This is how you work it out. Now, you could have a weak acid with its conjugate base, or you could have a weak base with its conjugate acid. Okay, so either one works. So what you do first, and you have to write this out, is you have to choose the acid that has a pKa value closest to the desired pH. So what that means is if I want my buffer to have a pH equal to 3, so I need my pH to stay 3, I want my buffer to have that pH, then I want to choose the weak acid component of whichever one that you're working with that has a pKa value that is equal to 3. Okay? Now remember what pKa is. pKa just means negative log of Ka. So if instead they give you Ka values, I want my Ka value to be equal to 1 times 10 to the negative 12. Okay, my language. It's not 1 times 10 to the negative 12. I was thinking about the next one that I was going to give you. So it is not 1 times 10 to the negative 12. God, I'm an idiot. It is 1 times 10 to the negative 3 is what we want. Okay, so Ka, I want it to be 1 times 10 to the negative 3, because if I take the negative log of this number, my pKa will be 3. Okay, so first and foremost, when I'm choosing a buffer, I have to choose the acid that's Ka value is closest to the pH that I want. If I want my pH to be 12, then I want to choose a pKa that is 12, or a Ka that is 1 times 10 to the negative 12. So that's the first thing that you have to do. Number 2, once I've chosen the correct acid and conjugate, and I have all of that stuff there, I'm going to mix my weak acid and conjugate base, or if I'm working with the other thing, my weak base and my conjugate acid. So I'm going to mix the weak conjugate component in a 1-to-1 ratio. I'm going to explain why that 1-to-1 ratio is important. And when I say 1-to-1 ratio, I mean 1 mole of weak acid to 1 mole of conjugate base, or 1 mole of weak base to 1 mole of conjugate acid. So I want those to be in a 1-to-1 ratio, and basically one of those are going to be a salt, right? Conjugate bases are salts, so it's going to be a solid more than likely. So you're going to have to dissolve that salt in enough water to make it dissolve. Okay, so you're mixing them in a 1-to-1 mole ratio. So that is what you do if you are given both components of your buffer, how you make that. And we're going to be doing this in lab. Now, if you are not given both components, you will be given this. So that's what this next one here is. I'm going to write that in blue. So if you are given only one component, so you're either given the weak acid or the weak base, okay, either one component, and you're given something strong in addition to that, how do you make a buffer? So you see how, like, we have something strong. Well, I don't need anything strong in a buffer. That's not what a buffer is. If I have a weak acid, what I need is my conjugate base. If I have a weak base, what I need to make my buffer is my conjugate acid. So how can I use either the strong acid or strong base to make those parts? If I have the weak base, what I'm going to do is add the strong acid to the weak base in order to make my buffer, in order to make my conjugate acid in this case. And I'm going to keep adding my strong acid to that weak base until I reach the pH that I desire. So if I want a very acidic buffer, then I'm going to keep adding that strong acid until I get to that acidic range. Okay, I'm basically going to make more conjugate acid, make more conjugate acid. You guys get the idea. If I have the weak acid portion, I need to make the conjugate base, right? Well, in order to make the conjugate base, what I'm going to do is add strong base to that weak acid until I have reached my desired pH. And as I'm adding my strong base to my weak acid, what I'm making there is my conjugate base part. Okay, so this is how we prepare buffers. It depends on what you are given, and they do ask this in free response, so we got to make sure we know how to justify that. So I'm going to get set up for buffer capacity and pH of buffer calculations, and then we should be rolling on our way towards the end of the video. All right, so now on to buffer capacity. Now, what buffer capacity means is it's the equal capacity to resist a change in pH, no matter if a strong acid or strong base is added. So buffer capacity basically means the ability for it to resist a change in pH. You want to have a buffer that has a very high buffer capacity. So there's two kind of main ideas with buffer capacity. I talked about on the how to prepare a buffer that you wanted a 1-to-1 mole ratio. So if I have weak acid and conjugate base that's present in my beaker, I want just as many weak acids as I do conjugate bases. So let's say I have 6 weak acids and I have 6 conjugate base parts there. Okay, this is just giving you an example of the main idea. This is a 1-to-1 ratio, 1-to-1 mole ratio. The reason why that is so important is because I can fight off I can neutralize just as much strong base, because my strong base is going to come in and react to the weak acids. Basically, I can neutralize 6 parts of strong base, right? And I could also neutralize 6 parts of strong acid. So basically, I can resist the same amount of strong base as I can strong acid. I can react with just as much. And so that's why a 1-to-1 mole ratio is very important. Now, if I want to increase my buffer capacity, make it even stronger. So this is nice because it's a 1-to-1 ratio. But if I want to make my buffer even more resistant to a change in pH, then what I want to do is increase the amount of weak acid and conjugate base that I have in a 1-to-1 ratio. So now I want to have, let's just say 16 weak acids for every 16 conjugate bases. Do you see how I'm still maintaining this 1-to-1 ratio? So what I'm doing is I'm increasing buffer capacity. Buffer capacity increases because now I can fight off 16 strong bases as well as 16 strong acids, whereas before I could just fight off 6 of each. So buffer capacity, 2 main ideas. We want a 1-to-1 mole-to-mole ratio of your weak to your conjugate. And secondly, as you increase both of those amounts in that 1-to-1 ratio, you're able to fight off or resist the change even better, so therefore your buffer capacity increases. So, another thing, pH of buffer calculations. This is the equation that you are going to use in order to calculate the pH. So let's talk about it a little bit. pH equals pKa. All right, we already talked about what pKa is. So that's negative log of Ka value. So you need to know that. If you don't have a Ka value, then and instead you have a Kb value, you're going to have to use that Kw formula in order to figure that out. And we talked about that in salts, I believe. plus log of A minus concentration, those brackets are there for a reason, is the concentration of A minus over the concentration of HA. This is exactly how you will see it on your equation sheet for when you take your test. So that's why I want to show it to you exactly like how it is. The A minus is representing the base. All right. So whether it's a conjugate base or a weak base, your base always goes on top. All right. The acid part, whether it's a weak acid or a conjugate acid, that will always be your denominator on the bottom. So it's the concentration of your acid on the bottom, the concentration of your base on top. And basically what you're going to do to calculate this mathematically, you're going to plug in those concentrations, divide the two, then take the log of that number and then add that number to the pKa value. And that will be equal to the pH that you have found. So remember how we said the pH desired, we want it to be closest to pKa of the acid. So this is why. It's because of this equation. The pKa is what drives the pH to get it closest to what it needs to be. So this is your buffer calculation. There's a couple of things that I'm going to point out to you guys. First of all, we'll talk about it in class. Never mind. I don't want to get into that yet. So we are going to talk about some really cool things that's happening here and make some connections with the titration curve when we talk about everything as a big idea. So this is your equation. We are going to go through the first two example problems on the back of this page together right now for this video. So there's two example problems we'll do. And then I'm going to do another video for the other example problems because that gets a little bit more complicated. So give me a second to get set up for those example problems on the back, and we will get rolling. All right, so here we are at our example problem. I wrote our equation down again. pH equals pKa plus log base concentration over acid concentration. So one of the main things that we have to do is we have to be able to read this problem and understand that we do have a buffer present and which part of the buffer we have. Like for instance, what's my weak acid? What's my conjugate base? Which is which basically. So we have 0.5 molar acetic acid. So acetic acid is a weak acid. And we have 0.7 molar sodium acetate. So remember how we said that you could have acetate ion or you could have it in the form of a salt. So the salt's sodium acetate. The sodium there is just a spectator. So this is the conjugate base part. So first of all, do I have a buffer? Yes. How do I know that? It's because I have a weak and a conjugate put together in solution. So now all I'm going to do is plug this into my formula. So pH is equal to pKa. So pKa is just negative log of this number here. So it's 1.8 times 10, that's a negative 5 right there. So if I take the negative log of this number, then I end up getting my pKa, which is 4.74, plus log, which one goes on top? The base goes on top. So that's this 0.7 molar. So 0.7 molar over the acid. The acid is the acetic acid, which is 0.5 molar. So now I'm going to work through my calculation. So notice how this is just a buffer solution kind of sitting there. I haven't added strong acid. I haven't added strong base in there at all. So I'm just making my buffer solution. It's just sitting there waiting for one of those invaders to come in. So that's why this calculation is pretty simple. So 0.7 over 0.5, take the log of that, add 4.74. You end up getting a pH that is 4.89. So that's our answer for example problem 1. Now let's do example problem 2. So we have a buffer solution, we have NH3, and we have NH4Cl. So we have a weak base, You need to get savvy at kind of picking apart what this stuff is. NH4Cl is a salt, right? And more importantly, it's an acidic salt. So therefore, it is my conjugate acid. So you kind of need to know how to do salts before you can move into here. Now, my pH is equal to pKa. Notice here how I have a Kb value. So what I'm going to have to do is use that Kw formula. Kw is equal to Ka times Kb. Kw is equal to 1 times 10 to the negative 14. So I'm going to take 1 times 10 to the negative 14, divide by the Kb, and that's going to give me my Ka value that I'm going to plug in right here. I cannot plug in a Kb or a pKb. It has to be pKa. So Ka ends up being 5.56 times 10 to the negative 10. And so we're going to take the negative log of this quantity, and it ends up being 9.25. So pKa is negative log of Ka, right? Negative log of this number, plus log of base over acid. Oh, don't forget, it's base over acid. So our base component is the NH3, so that's 0.25. Our acid component is 0.4. It's the NH4Cl, so 0.4. And we are going to do that calculation. I forgot to write log in here. Sorry, I'm very forgetful today. So log, blah, blah, blah. Divide those, take the log, add to 9.25, and you end up getting a pH of 9.05. So that is how we find the pH of a buffer just sitting by itself before we've added any strong acid or strong base to that. So we're going to go further into another video later on. We're going to talk about it in class as well. I really want to make sure that you guys understand this concept. They tend to ask a lot of buffer type questions, but it's easy as long as you understand it conceptually. The main focus is to understand buffers conceptually, and then the math will come together. So I hope this is helpful. If you have any questions, do not hesitate to ask, okay? So I'll talk to you later. Have a good one. I hope you enjoy buffers.